Unit 6, Lesson 4, Best Fit Line, which I briefly talked about in Unit 3, or Lesson 3. So we kind of have an idea of what it is. So here's a scatter plot that shows weights and fuel efficiency of 20 different types of cars. If a car weighs 1,750 pounds, would you expect its fuel efficiency to be closer to 22 or 28 miles per gallon? Explain your reasoning. So if we have two dots really close. If we were to draw a line best fit, we would go through majority of the points, have about the same amount on top and on bottom. So I would draw a line, I don't know, maybe something like that. Looks like it could be a little bit off. So would you expect the weight of this car to be closer to 22 or 28? Well, based on the graph, I would say 22 miles per hour because that goes through the line best fit. Write down your reasoning of why. .2. I have to move my camera up so you guys can see it all. So here's a table that shows weight and price of 20 different diamonds. I believe we saw this graph in lesson 1. So here's the table. The scatter plot shows the price and weight of 20 diamonds together with the graph of, so this line right here, together with the graph of y equals 5,520x minus 1,091. The function described by the equation is modeled with the relationship between weight and price. The model predicts the price of diamonds from its weight. These predicted prices are shown in the third column of the table. So this blue line is not this, the line of that equation. It's just the equation that they use to find the weight. Two diamonds that both weigh 1.5 carats have different prices. What are their prices? How can you see this in the table? How can you see it in the graph? So if I went to 1.5, so to see it on the graph, I go to 1.5 and I go up. We have this one and we have this one. If I were to find the table, I'm going to find the one that's 1.5, which is right here. And I have these two. So the prices are, actual prices, 7,474 and 5,904. So for the table and the graph, both of them, we went to the X value, which is weight, and we found 1.5 and then found its corresponding price. Number 2, the model predicts that when the weight is 1.5 carats, the price will be 7,189. How can you see this in the graph? Can you see this using the equation? So if we were going to use the equation, we plug in 1.5 to our X value, see what we get. On the graph, I believe we almost see it with this line. So we would see it with a line best fit. On the graph, it's about on the blue line. On the next page, number 3 says one of the diamond weighs 1.9 carats. So if on my table, I can see it way down here. You can't see it in the picture. What does the model predict for its price? How does it compare to its actual price? So our model predicts 9,541. So if we go here, 1.9, probably this one. And it's really close. It's less than $200 off. It's about $150 off. There is about $150 difference. Find the diamond for which the model makes very good prediction of the actual price. Can you see it? This in the table, in the graph. So we have a couple that are really, line goes right through them. We have one that costs $6,000 about. And it's somewhere in between there. So let's find the one really close to 6,000, maybe this one. So the diamond that weighs 1.3 carats. And there's another one. So this one is maybe 5,500. Let's find one close to 5,500. This one right here. 1.2 carats. This one is off by $11. So that one's really close. Number 5, find a diamond for which the model's prediction is not very close to the actual price. So which one is farthest off? I almost want to say this one that we already circled. Looks like it's farthest off. So it would be, and it's kind of hard to pick out what one it would be. So maybe we'll do this. And draw an arrow. Shows what one, because we could put the diamond that weighs 1.5 carats, but really there's 2. I feel like that's the one that's most off. It's over $1,000 off. I guess this one's right about $1,000 off too. This one's right about $1,000 off. So I guess there's a couple of them that are about $1,000 off. We could also make the line keep going. Point to that one because that one's over $1,000 off. So we found 2. 4.3, the agony of the feet. Here's a scatter plot that shows lengths and widths of 20 different left feet. Okay. Estimate the width of the longest foot and the shortest foot. So the length of the longest foot is just over 30 centimeters. Its width is 11.8. Longest equals about 11.8 centimeters. Wide. Not wide, it's just wide. Shortest equals about, I think this is the shortest foot, maybe. I go with this one as probably the shortest. Its width is about 9.2. Estimate the length of the widest foot. Well, I think this is the widest foot. So about 30.5. 30.5 centimeters long. And the narrowest. Here's my narrowest foot. 24. This is probably 25 right here. So 24 and a half maybe? Long, not lod. Lond. Here's the same scatter plot together with a graph of a model for the relationship between foot length and width. Circle the data point that seems weird when compared to the model. This one seems weird because it's not even close to the line. What length and width does this point represent? Well, we said it was about 24 and a half and 7.8. So we're going to do our x first because we need the point. 24.5, and it's width 7.75. About, remember, this is our x and our y when we are labeling ordered pairs. Oh, this weird point that we had, this is called an outlier. It can skew your data just a little bit because it doesn't really fit this information up here. So we have our lesson summary, line best fit, and then, we have this outlier. Sometimes a data point far from the other points or doesn't fit the trend of the other points, it's called an outlier. So in this graph, you might say this one's an outlier because it's not really as close as the other ones. It really still isn't that far from it. Practice problems. A scatter plot shows the number of hits and home runs for 20 baseball players who had at least 10 hits last season. So we have this, we have this. So use the graph in the table to answer the questions. Player A had 154 hits in 2015. Hits, 154. How many home runs did he have? Well, he had 26. Home runs. How many was predicted? 21.6 was predicted. Player B was the player who most outperformed the prediction. So that means this number is a lot bigger than this number. So that one does not perform. This one outperforms. This one doesn't. This one outperforms. No. This one does. No. So this one outperformed it by 9. This one outperformed it by 8. So I would say this one. How many hits did he have? He had 57 hits last season. Okay. What would you expect to see in the graph for the player who hit many fewer home runs than model predicted? It would be an outlier. It wouldn't fit the trend. Liar. 2. Here's a scatter plot that compares points per game to free throw attempts per game. For baseball, the model represented y equals 4.413x plus 0.377 is graphed with a scatter plot. Here x represents free throws per game and y is points per game. Circle a point that appears to be an outlier. Say this one, it is the farthest from the line. What does it mean for a point to be far above the line? It performed better. He, she, than predicted. Based on the model, how many points per game would you expect a player who attempts 4.5 free throws per game to have? So we go here, about there. Round your answer to the nearest tenth of a point per game. So we're about here. This doesn't count up by anything in particular, maybe 20. One of the players scored 13.7 points per game with 4.1 free throw attempts. How does this compare to the model? So 4.1 is back here, and 13 is here. So I'd say it's probably that one. Performed not as good as the model predicted. Oh, you can't even see that. There you are. And that is the end of the lesson 4 video.